Hi everyone. So as promised, this is a video on 5.4. I'm going to try to make it quick because essentially we've covered everything we need to know. Everything we're doing today and even tomorrow is going to be different variations of derivative questions with exponentials. Tomorrow being more word questions, so applications. So today, if you take a look at the handout, we've got A, let's do a bit of 3B, turning the little bit of 4C, turn the page, 5AD, and 6-8. Things that I think are a bit more of a challenge. Of course, there are answer keys attached to your work, but if you have requests for full solutions, just save them or send me an email. Maybe I can make another video and so on and so forth. Okay, so without further ado, here we go. Differentiating. This question one, essentially the first page is a review of 5.3. So if you have trouble with it, you may want to consider going into 5.3 again. Okay, I'm just going to go quick because this shouldn't take us too much time. The derivative, or dy over dx, is going to be equal to, it's an exponent, so copy this exact thing down, multiplied by the ln of the base, multiplied by the derivative of the exponent, so chain rule. So that would be negative 3x squared. And that would be the end, but it's also always nice to have a habit of cleaning things up. I'm going to keep these two together because those are numbers, regular constants, and then the variable, and then the exponent. So it's sort of like a coefficient. So negative 3, oops, not ln, but ln 2, x squared times 2 to the power of negative x to the power of 3. Okay, it's going to get messy like this, so hope you're getting used to it. Okay, I'm going to keep going. So again, if this is moving too fast, know that the video is going to be found on Brightspace. You do what you need to do. Let's keep going. Question 3b. I thought this would be a good way to segue or bring in our sinusoidals. Please remember the derivatives of sine is cos and the derivative of cos is negative sine. So the same rules apply. Y prime. It's an exponent, right? The variable is in the exponent. And so you've got copy the power just as is, multiplied by ln of the base, which is going to turn into 1, multiplied by the derivative of cosine. And that's that. I'm not going to write this anymore from now on because it is a waste of our time. If the base is e, I hope that you feel that way too and you don't have to write this. But it will come with practice. If you are struggling to understand why it's disappearing or reappearing, or I'm switching back and forth from one method to another, stick to this. Keep on writing it until you realize, oh, I don't need to. Shortcuts come from practice and laziness, not because it's the proper quote unquote way to do. Okay, so simplified, this becomes negative sine x times e to the power of cosine x. There you go. Hope that's good. Let's move on. Question 4 had one. Yeah. This is, let's develop an eye of breaking down functions. This in itself is a function. And since this is also something else, there's going to be a derivative to this that's other than a 1. The variable x is also found in another function, so you know that it's going to be product rule. So derive. So this time I'll write dy over dx. Derive the first. So you know what? How about we set it up so that your eyes can focus on the correct area? This is the first function. This is the second function. Okay? Derive the first, which is copy down times ln e times the derivative of the exponent. Leave the second function all alone, plus leave the first function all alone, derive the second function. That will give you your full mark, and probably cleaning up or even factoring will give you the second one. And once again, there's nothing necessarily wrong with it. I am going to bring the negative in the front and clean this up. But it's a really good habit to look for commonalities or common factors because sometime in the future that might be really useful to you. Okay, so there's a negative 1, e to the power of negative x. I will factor out negative e to the power of negative x, leaving me cosine x plus sine x. Okay, so get into that habit. So this is correct. This is a lot more useful, I think, for the future. Okay, I'll leave it to the substitute teacher to pause if the students need a bit more time, but I'm going to move on for the sake of the video. Differentiate with respect to x. In other words, please find dy with respect to the change in x. Okay, here we have a composite function. We have a function inside a function, and that function happens to be an exponent. Hope you're good. So chain rule is deriving the outside and then derive the inside. The derivative of sine e of x is equal to, how about I stick to it proper, e to the power of x times the cosine of e to the power of x. There it is. Okay. As a quick note, this being chain rule, I need to derive the inside. If the inside happened to be like 2 to the power of something, you know that that's going to have ln 2 blah 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 as well. Okay, so again, it comes with the comfort or how comfortable you are deriving e to the power of x. Let's keep moving. B, there's your hint. You can try it. D, ooh, okay, let's do it. We have a function, a square root function as my exponent. So the derivative of that is going to be some kind of polynomial derivative. Yeah, let's try it. D, for the sake of space, I'll do it here. dy over dx is, leave the exponent or leave the power as is, times ln of the base, which is 1, times the derivative of this. So in my head, I'm going to pretend this is power of half. So the derivative of the exponent is going to be 1 over 2, x squared plus 1, subtract 1 from the exponent, and then chain rule, derive the inside. Wow. Suddenly it sort of blew up in your face, huh? I'm going to clean this up. I have a half and a 2, so this will effectively cancel out. X squared plus 1 is a square root in the denominator. I have x in the numerator. So this is going to be x times e of x squared plus 1. And all of this is there. Okay. Once again, I'll leave it to the substitute to pause if the students need it. I will move on. Differentiate and simplify. It's getting pretty big here. I've got a function. It's not e. I've got a polynomial, a cubic. And when I derive, it's going to use a quotient rule. So let's try it. This is letter B. dy over dx is going to be, derive the first, which means copy as is, ln of the base, derivative of the exponent. That's the derivative of the first function. Leave the second function all alone, minus leave the first function all alone, times the derivative of the second function, all over the second function squared. So that's to the power of 6. So once again, this would be correct, so you get your mark, but the next mark would come from cleaning things up and simplifying. What are some things that I see common? I see 2 to the power of 4x and 2 to the power of 4x. I also see that I can reduce x to the power of 2, x to the power of 3, x to the power of 6. So this would be X to the power of 2 is gone. The exponent is gone, is just an x, and this becomes a 4. Let's clean it up. If I factor out 2 to the power of 4x, what I'm left with here is 4 ln 2 times x. And what I'm left with here is minus 3. All over x to the power of 4. Right? That's it. Just, shall I dare? Let's take a look at the answer key. Question 6C. Oh, it looks to me that I did not factor out 2 to the power of 4x. Again, that's totally fine. But I think it's a good habit to look for that, just in case, let's say, for whatever reason, we want to know what the max and min is, and we need to make the derivative equal to a 0. Then we can check, how do I make that a 0, and how do I make that a 0? It's so much easier to do it that way. So I think it's a good habit. Case in point, take a look at question number 8. Once again, please pause if the students need it. Find the local extrema for y equals this. So, bringing back our previous chapter, when you're talking about extrema, that's basically max or min. And how do we identify max or min? We know that the slope is going to be a 0, which means when is the derivative equal to a 0? That's what we need. So let's find it. dy over dx is derive the first, leave the second all alone, minus leave the first all alone, derive the second, which means the power is copied down, times ln e, which is 1, times the derivative of the exponent. And that is also wrong. It's supposed to be a plus. That's my bad. For some reason, I kept thinking quotient rule. But there it is. And I need to know when this is equal to a 0. So I think you get it. It's in your best interest to factor. So I see 2x as a common. I see e to the power of negative x squared. That is common. So 2x I will factor out. And e negative x squared I will factor out. It leaves me with the first term being a 1, the second term being a negative x squared. Okay, so when is that equal to a 0? Well, that means 2x has to be a 0, and so x has to be a 0. This one, it will never equal a 0, because exponents will never equal a 0, and so I don't have to worry. This one, when is 1 minus x squared equal to a 0? It is when x squared equals to a positive 1, so x must be plus or minus 1. There it is. So if this was an early chapter, that will be the end of it. You know that there is some kind of max or min when x equals -1, 0, and positive 1. But we know that sometimes having the critical numbers is not enough. We want to find what the actual extrema are. So I'm going to test it. -1, 0, 1. And my function derivative and my original function. So let's do it. A really big negative number, that means a negative times something. Wait, a negative times e to the power, still a positive, because remember, as a exponential, right, it wouldn't be a 0. Oh, sorry, it wouldn't be a negative. And that negative in front of the x squared means I have horizontally flipped. So it's still never going to be a negative value. So a big negative x means that's a negative times a positive times a negative. Negative, positive, negative, that's going to be plus. A tiny number that's negative, that's still a negative, that's positive, that's going to be positive, so this will be minus. We have a tiny positive, 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 and a huge positive, a huge positive, and a huge positive subtraction, that's going to be a negative. So we've got the curve going up, before going down, before going up, before going down. These are, in fact, maxes and mins. Okay, so find the local extrema for y equals that. It doesn't ask for what the max extrema is. I just want to find the local extrema. So therefore, the extrema are found at x equals -1, 0, and 1. Done. Okay. I believe I have lots of questions assigned to you. So going to our Brightspace, there are exercises, that I've attached for you. There are more questions for equations of tangent lines. There are more spicier derivative questions. Here are some thinking style questions where it's not immediately obvious. Determine all values of a for which this satisfies the equation. I'd like you to give it a shot. And I'd love to take up any of your questions that you have on Friday. So the rest of class, it will be a work period. Do your very best, and I do hope you come with questions. One, it'll show me that you have been responsible and faithful to your work. And number two, running into problems means that you're actually learning. So I'm excited to hear from you there. Okay? Best of luck, suffer well, and I'll see you Friday.